Hello everyone, and welcome to a couple of examples of applying Newton's second law to purely rotating objects. Number one, we're going to look at this huge shield door at the Lawrence Livermore Laboratory. At one time it was the heaviest hinge door in the world. It had a mass of 44,000 kilograms, which means it weighed around 100,000 pounds. It had a rotational inertia of 8.7 times 10 to the fourth kilogram meters and a width of 2.4 meters. That's this distance right here, from hinges to edge, about 2.4 meters. Neglecting friction, which means that we have to assume here that these are perfect hinges, and you can see here the little pipes and things running. They're probably some sort of hydraulic hinges. What steady force applied at the outer edge and perpendicular to the plane of the door, like you see this young woman here in this picture, what force can move it from rest through an angle of 90 degrees in 30 seconds? So we're going to rotate it through 90 degrees, about a quarter of the way around, and take an entire 30 seconds. Pretty long time. So what force is that? Well, first of all, let's draw a quick little diagram. Here's looking down at the top of the door. And there is the axis of rotation, right? Those are the hinges, if you will. She is applying a force down here, which is perpendicular to the door. Right? That force. Now, that force, of course, applies a torque. And by Newton's second law, that net torque has to be equal to the rotational inertia times the angular acceleration. And notice that that torque will cause it to rotate clockwise, and hence it is a negative torque. Well, the force that we're looking for is hidden inside of the torque. And while we know the rotational inertia, we don't yet know the angular acceleration. So that's our next step. What is the angular acceleration of this door? Well, here's a key thing. Since it says it's a steady force, that means it's constant, and it's going to be a constant distance away. That means that the torque that results is constant. And if the net torque is constant, then the resulting angular acceleration is uniform. And if it's a uniformly accelerated motion, we can use the kinematic equations. Which one? Well, let's see what we know. We know that it's going to rotate through an angle of 90 degrees, except I want to convert that to radians because I want the units to work out correctly. So 90 degrees is about a quarter, right, of the way around. And since all the way around is 2 pi radians, a quarter of that is pi halves radians. Now notice here, I also made it negative. Why? Because again, it is rotating clockwise. The time here is 30 seconds. And then here's a key, can move it from rest. So the initial angular velocity, 0 radians per second. So knowing these three things and looking for the acceleration, we would of course use the ever popular third kinematic equation. Angular displacement equals initial angular velocity times the time plus 1/2 the angular acceleration times the time squared. The initial angular velocity times the time would of course be 0, so multiply by 2, divide by t squared, and you get the angular acceleration. Plug in our numbers, and notice we will have units of radians per second. Don't forget to, second squared, sorry, don't forget to square that. And we get an answer of negative 3.49 times 10 to the negative third radians per second squared. Now remember, that's really a radian per second every second. So that means that the door is going to accelerate or increase its velocity by negative 3.49 times 10 to the negative third radians per second every second. The negative is because it's going to go clockwise. So that's really slow. It's not a very fast acceleration at all, but that's why it's going to take her 30 seconds to rotate through 90 degrees. So we now know the angular acceleration. We take the torque, and remember, torque is of course RF sine theta, but theta here, here's R, right? Here's F is 90, and the sine of 90 is 1, and the torque is negative because it's clockwise. So we solve for F, and we get that the force is equal to negative I alpha over R. Plug in the numbers that we were given, or the angular acceleration we found, and notice the negatives cancel. Notice here, unit-wise, this meter cancels with one of those. Radians disappears because it's a name, not really a unit. So we end up with kilogram meter per second squared, which is, of course, a newton. So we end up with a force of only 130 newtons. Now remember, a newton is a little less than a quarter of a pound. It's like 0.22 pounds. So this is really only about 28 pounds of force. And so I think any of you could apply a 28-pound force for 30 seconds. And again, remember that one of the key things here is there's only one torque. There is no frictional torque. So we're assuming perfect hinges. Because if there was any friction at all, it would be huge because of the large weight of this door. So there's a little example of applying Newton's second law to a purely rotating object when we had to do a little kinematics work along the way. So here's a little more complex of a situation, more than one force. Here we have a cylinder, mass 2 kilograms. There's 4 forces acting on it. Here are the magnitudes of those 4 forces. And they are at 2 different distances from the axis of rotation. F1, F2, and F4 are all a distance r2 away, which is 12 centimeters, which, by the way, I'm going to convert into 0.12 meters so that our units check out. F3 is acting kind of a little less than halfway from the middle. Right? It's R1, which is 5.0 centimeters. Now, technically, there would be 2 other forces acting on this cylinder. There would be a force of gravity acting from the center of gravity, and there would be a normal force that would balance that out to keep it from going up and down, right, so that it just spins. But neither of those forces apply a torque anyway, because they act through the axis of rotation. So you might put them on here, but in this case, we're going to leave them off because they don't really affect anything rotationally anyway. So, by Newton's second law, the net torque provided by these 4 forces has to equal I alpha. And therefore, the angular acceleration we're trying to find is the net torque over the rotational inertia. So let's take those pieces one at a time. To figure out the net torque, let's complete a torque bar graph. Remember those that we used back in the static equilibrium section of this unit. Well, we have 4 forces, so we have the possibility of 4 torques. Right? Again, I'm going to neglect the normal force and gravity because they act through the axis of rotation. In fact, not even all 4 of these apply a torque. Look at F4. It extends back through the axis of rotation. So you're pulling straight out on a disk. And think about pulling straight out on a disk or a door. There is no turning effect because of that. So torque 4 is 0. So now we just have to calculate torques 1, 2, and 3. And I'll show you the equations in a second, but let's talk about direction first. F1 would make this thing rotate counterclockwise, and hence torque 1 will be positive. F2 and F3 would make this object rotate clockwise, and therefore torque 2 and torque 3 will be negative. And we'll draw them down here. Okay, so keep that in mind. So how are we going to find how big those torques are? Well, we can use the torque equation, of course, RF sine theta. If we go back to the diagram, notice that all of them are perpendicular. So in every case, we have the lever arm, the perpendicular R, and we have theta is 90. And the sine of 90 is 1, so each torque is simply R times F. Just make sure you get the right R and the right F. So torque 1 is R2 times F1. If you don't believe me, go back and look at the diagram. That's 0.12 meters times 6 newtons, or 0.72 newton meters. Now you may notice that over here, in order to make this quantitative, I've put positive 0.80 newton meter torque at the top and negative 0.80 newton meters at the bottom. So each one's roughly about 0.2 newton meters. So this would be about there, would be 0.72. Torque 2 is R times F2, R2 times F2, which works out to be about 0.48 newton meters. Now remember, from our earlier discussion, force 2 would make it rotate clockwise, so torque 2 is negative. Torque 3 is only R1 F3, so that's 0.050 meters times 2.0 newtons, or 0.10 newton meters, and, like torque 2, F3 would make it rotate clockwise, and so it is negative. So the net torque would simply be the vector sum of the 4 torques, and torque 4 is 0. Right? So I made these negative because they're going to make it rotate clockwise. Put your numbers in, and you get a net torque of positive 0.14 newton meters. Now, why is it positive? Because it would make it rotate counterclockwise. Keep that in mind for our answer in a moment. So, the rotational inertia, this isn't one that you have to have memorized, okay? But I gave you a sheet of common object rotational inertias, and certainly this was on here. A solid cylinder rotating about an axis through its center is 1/2 mr squared. R2, by the way, the entire radius of the cylinder. So that's 1/2 times 2.0 kilograms times 0.12 meters squared, which works out to be a nice small 0.0144 kilogram meters squared. Well, if the net torque is I alpha, then alpha is net torque over I, so plug in the two things we calculated, and let's check out the units. We have Newton meters over kilogram meters squared, so one of the meters cancels. And right now you might say, but wait a minute, that doesn't look like acceleration units. But remember, a Newton is a derived unit. It stands for the force required to make a 1 kilogram object accelerate at 1 meter per second squared. So a Newton is a kilogram meter per second squared. Kilograms cancel, meters cancel, and we're left with per second squareds. But remember, since this is an angular quantity, right, we need to know what it's rotating through, and that would be radians. Remember, radians are there when you want them. You can take them out when they're not. Radian is really a name, not a true unit. Okay? It is the ratio of the arc length to the radius, if you remember our very first lab in this unit. So, calculate the numbers, and you get 9.7 radians per second squared. And since it's positive, that means that the direction that's asked for in the problem is, of course, counterclockwise. So what does that mean? Well, since it's going to start from rest here, we have to assume so given the statement of the problem, that means that every second that goes by, the angular velocity is increasing by 9.7 radians per second, counterclockwise. Eventually, we will apply this idea of Newton's laws to rolling objects, but we'll get there. For now, let's start out with just rigid objects rotating about a fixed axis. So I hope you enjoyed these two examples of applying Newton's second law to rigid objects rotating about fixed axes.